In this video, we are doing a quick recap on one-to-one functions. So we'll do a couple of examples where we have one-to-one functions, and we'll also take a look at how to show that a function is not one-to-one. Let's do, before we start with an example, a quick recap of what it means for a function to be one-to-one. So if we have a function, let's say f from some set A to a set B, we will say that f is one-to-one, or we will also say injective, if we have the following. So if, let's say, for two different elements or distinct elements in the domain, let's say x1 and x2 in A, if we have that x1 is not equal to x2, meaning we have different inputs, then if it's one-to-one, it means we will also get different outputs. That's the main idea. So f at x1 will not be equal to f at x2. We can also see this in the opposite direction. If we look at the contrapositive of this statement, it says that if we have the same output, so f at x1 is equal to f at x2, meaning the height at x1 and x2 is the same, then x1 has to be equal to x2. What this means graphically is actually that the height never repeats for any x value. If it attains a specific height at one x value, it will never again attain that height at any of the other values in the domain. Now, in terms of this function, f from R to R, defined by f of x is x squared minus 4x. In some of the previous videos, we've taken a look at this function. We've made a quick sketch. This function is not one-to-one because it is a parabola. It's symmetric around the axis of symmetry. This is, if I remember correctly, x is equal to 2. We'll sketch the graph to confirm that now. But because it is symmetric, there is a branch on the left and there's a branch of the parabola on the right or where the height is being repeated. So let's do a quick sketch. We can get our counterexample straight from the sketch. If we take a look at where it intersects the x-axis, we are going to say let the function value be 0. So let x squared minus 4x be 0. We can take out a common factor of x. We will have left x minus 4 equal to 0. So it cuts the x-axis at 0, and it cuts the x-axis at 4. So there we have our parabola. It's upward facing, so it looks something like this. One of the tests that we did very much earlier, I think already in high school, was the horizontal line test. So if we could draw a horizontal line through the graph and it cuts the graph in more than one place, it means the height is actually repeated. So suppose we take the horizontal line y is equal to 0. We've already seen we get that we have an intercept at x is equal to 0 and at x is equal to 4. So this is exactly our counterexample to show that this is not one-to-one. So here for our counterexample, we can say let x be equal, or let x1 be equal to 0 and x2 be equal to 4. They are clearly from the domain and they are not equal to each other, but f at x1 is equal to f at 0, which is 0, and f at x2, which is f at 4, is going to be 16 minus 4 times 4, which is 16, equal to 0. So we have two different x values being mapped to exactly the same y value, and therefore we can make our conclusion: f is not 1-to-1. Here's another example that we looked at previously. F of x is equal to the square root of 1 minus x squared. We would like to determine whether or not this is 1-to-1. So let's do a quick sketch here on the right. Again, what does this function or this graph look like? Well, if we square both sides, I'm going to use y in the place of f of x. If we square both sides, we get y squared is equal to the square root of 1 minus x squared squared. And so the square root and the square cancels. We can take the negative x squared over to the left. So this gives us x squared plus y squared must be equal to 1. And this is a circle. Again, because we started with the positive square root, y is positive, meaning not negative. It could be 0. We are only looking at the top half of this circle, centered at the origin, radius 1. Now, again, let's try to do the horizontal line test. I'm going to take the most obvious horizontal line here. If we use the x-axis, we can see that over there and over there, this is where x is equal to negative 1 and 1. We have a horizontal line that cuts our function in more than one position. So again, for our counterexample, we are going to say, let x be equal to negative 1. Let's call it x1, and x2 equal to 1. Then f at negative 1 is going to give us square root of 1 minus 1, which is 0. And f at 1 gives us exactly the same y value, square root of 1 minus 1, which is 0. So therefore, f is not injective or 1-to-1. We get two different elements from the domain, negative 1 and 1, and they both get mapped to exactly the same element in the range, in the codomain, which is 0. Here's another example of a function that definitely is not 1-to-1, because the height, no matter at which height we take a horizontal line through the cos graph, we get infinitely many repeats. So we can do a quick sketch just to get an idea of what we would like to use as a counterexample, but we can also use this to confirm it definitely does not pass the horizontal line test. There we have y is equal to cos of x, and you can see when you are drawing the graph, infinitely many times the height is going to be repeating. So we just need to pick one example where this is going to be the case. Again, if we take y is equal to 0, if we draw a horizontal line through here, just to show you how many counterexamples we will get, every single pi radians we will get a counterexample. So here we can just focus on the very first two that we encounter. where is cos of x equal to 0? Well, if x is equal to pi over 2, let's take this as our first value. Let's say x1 is equal to pi over 2. And let's pick our second x value, x2. We can choose, do we use 3 pi over 2 or negative pi over 2? It doesn't matter. Any one of these will do the trick. So let's say x2 is minus pi over 2. Well, then the function at x1 will be cos of pi over 2, which is 0. And the function at x2 will be cos of negative pi over 2. But again, this will also be 0. So we have two distinct elements in the domain being mapped to exactly the same element in the range, and therefore f is not 1-to-1. How do we go about proving that a graph is actually 1-to-1? Here we have a very popular or well-known graph. This or function f of x is equal to ln x. We know that this is 1-to-1 because it has an inverse, y is equal to e to the x. But we want to show this analytically. Okay, so I'm just going to do the sketch of the graph just so we can confirm. There is the function f of x is equal to ln x, cuts the x-axis at x is equal to 1. It is a strictly increasing function, meaning no y values are ever repeated for distinct x values. If we were to draw anywhere within the range, which is the full R, any horizontal line at any height, it would only cut the graph at one specific point. How do we prove this using our definition? So what we are going to do is we are going to assume that f at some x1 in the domain is indeed equal to f at x2. So here x1 and x2 are elements of the domain R+. Okay, if this is the case, then we can plug this in. It would mean ln of x1 is equal to ln of x2. We can take e on both sides, so here we will get e to the power ln of x1 must also then be equal to e to the ln of x2. Just going to put brackets around this just so it's clear. And now e and ln are inverse functions of each other. So e to the ln of x1 will simply be equal to x1. And the same on the right-hand side, e to the ln of x2 is simply equal to x2. And so we've assumed f at x1 is equal to f at x2. We get the same output. But if we apply this to this specific function, this means that x1 has to be equal to x2. Meaning, again, the contrapositive, if they are different, the function values will also be different. So if this is the case, we can make our conclusion, which says therefore f is 1-to-1.